Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on the structure of the atom. In our last lesson, we reviewed the major discoveries that were the basis for the modern atomic theory. We identified some of the key experiments that led to discoveries of the constituent particles of an atom. We also reviewed the modern atomic theory to provide a basis for comparison between what was discovered many years ago and what we consider to be true today. In this lesson, we will continue our review on the structure of the atom. We will begin with each of the atomic models studied so far in this unit. Let us start with an activity. On screen, you will see some of the atomic models we have studied in this unit. Can you identify them all? Please write your answers down now.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. I am sure you had no trouble with this activity. If you labeled the atomic models correctly, then you will have found the following. The first model is the Dalton atomic model. John Dalton thought of atoms as solid, indestructible spheres. He called it the billiard ball model. The second is the Thomson, or plum pudding model. After learning that atoms contain electrons, J.J. Thomson proposed a new model of the atom. Thomson proposed that electrons were embedded inside a positively charged sphere, just like plums in a pudding. The third is the Rutherford atomic model. The Rutherford model of the atom has a small, dense, positively charged nucleus around which electrons whirl at high speeds and at relatively long distances from it. Ernest Rutherford compared the structure of an atom with the solar system, saying that the nucleus corresponds to the sun, while the electrons correspond to the planets. This is also called the planetary atoms. The last is the Bohr model of the atom. Niels Bohr proposed an atomic model in which the electrons moved around the nucleus in circular paths called orbits. He assumed the electrons to be moving around the nucleus in a circular orbit as the planets move around the sun. Were you able to label each of these correctly, students? If so, well done. Labeling these models correctly is critical to your studies. Make sure you review your answers with your teacher after class if you are still having difficulty. Now we properly understand the historical views of the atom. Let us focus on the quantum mechanical model in our next activity. Please complete the following statements. A list has been provided with the terms to make it easier to complete the task. Some terms may apply more than once, so do not be afraid to reuse a term you think is correct. You may begin.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. Let us now fill out the statements to see if you have correctly completed each one. In the quantum mechanical model, electrons cannot be pinpointed and instead are described in terms of probability. This model introduces the concept of sublevels for each main energy level. They are designated by the letters S, P, D, and F. Regions of space around the nucleus in which electrons can be found are called orbitals. Each orbital can accommodate a maximum of 2 electrons. The amount of sublevels in each shell depends on the value of the principal quantum number, represented by the letter N. Were these your answers? If so, great job! In class, you were introduced to the concept of electron configuration. This is a characteristic of measurement in the quantum mechanical model. We use this to determine the ground state electron configuration of different atoms. This is the lowest possible energy state in which electrons will orbit the atom. Remember that electron configurations are designated by a coefficient, which shows the main energy level. Then, we specify the letter that denotes the sublevel that an electron occupies. This is followed by a superscript that shows the number of electrons on that sublevel. Remember that electrons are arranged according to the diagonal rule. This is particularly useful when trying to resolve the electron configurations of atoms with atomic numbers greater than 18 because of their complexity. Students, let us do an activity to see if we can identify whether a given electron configuration is accurate. On this list, there are several configurations, but only some of them are correct. First, identify whether or not they are accurate, and if they are inaccurate, correct the configuration. You may begin.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. Let us go over each of the configurations individually. The first configuration is inaccurate. The mistake in this configuration is in the 2p subshell, which should be completely filled by electrons before applying the remaining amount to the 3s subshell. This means that the correct configuration does not have a 3s orbital and can be expressed as 1s2, 2s2, and 2p6. The second configuration is accurate. This is the ground state electron configuration of aluminium. The third configuration, the ground state electron configuration of neon, is also accurate. The next configuration is inaccurate. The flaw in the configuration is at subshell 3p, which has not been completely filled before the 4s and 3d subshells. Thus, the correct configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d1. Were you successful in finding the right answer, students? If any of your answers were incorrect, please compare your answers to those of your classmates. That is all we have time for today. In this lesson, we have identified the different atomic models visually. We have also reviewed the characteristics of the quantum mechanical model of the atom. We reviewed the concept of electron configuration and practiced identifying inaccuracies in these configurations. I hope you have found this useful. Until next time, thank you, teacher. Thank you, students.